Okay, so the left-hand rule approximates a function with constant functions on small subintervals and then computes the definite integral of these constant functions. Okay? The trapezoid rule approximates a function with a linear function on small subintervals, then computes the definite integral of those linear functions. And so we see a pattern here. Now with the Simpson's rule, this approximates a function with quadratic functions on small subintervals and then computes the definite integral over these quadratic functions. So if you're kind of lost in that paragraph and words aren't really doing it for you, let me show you in a picture what I'm talking about. Okay, so left-hand rule, midpoint rule, right-hand rule all kind of work the same. They approximate functions, integrals with constant functions. Okay, so what do I mean by that? So say I have this function here and I want to use a left-hand rule with one rectangle to approximate the area. All you need to use the left-hand rule is a single point. A single point is needed to construct a constant function. Why? Because if I have one dot, I know a constant function is the horizontal line that passes through that one dot. Okay? So with a linear function approximation, well, to draw a line, I need two dots, okay? 2 points, draw a line, and then I can use that to approximate the area. All right, so 2 points to make a linear function, a single point to make a constant function, okay? And so this linear function, we used the trapezoid rule. Remember, we formed a trapezoid, and we found the area doing that. And we found that that trapezoid rule was actually way better than using rectangles. Okay, the trapezoids seem to fit the curves a little bit better, and you didn't have to have too many trapezoids to get a good approximation. Now, to go one step further than the trapezoid, instead of using a constant or a linear, which has different slope than the zero, I use a quadratic function for the top part of my curve, okay? And so if I do that, to use a quadratic function, I need to come up with a third point, all right? So a third point allows me to make a quadratic functions. So in general, so basically what we're saying here is to make a constant function, I need a single point. To make a line, a linear function, I need 2 points. To make a quadratic for my top of my so-called pseudo rectangle, I need 3 points. Okay, so these are the different techniques that we will talk about in Calculus 1 for approximating integration. All right, so to approximate a definite integral, you could use a constant, you could use a linear function through trapezoid rule, or you could use the quadratic function through Simpson's rule. Okay, so how does this work? Simpson's rule. Now, look, if you are not a math major, or like you're just looking for, a bruising, then you can watch, the rest of this proof, and hopefully it won't bore you to tears. But if you're like, math is your major, you want to go into this is a good thing to watch, because it's going to kind of give you an idea of what's to come whenever you get into higher level math. It's all about proving things are true, right? So it's not just, oh, here's the formula, great. But if you're, engineer or science major or whatever other field, and you're not going in to study higher mathematics, then you can skip over this Simpson's proof part and you won't hurt my feelings, okay? So here's how you prove it, all right? So if you don't get it, that's fine. Don't freak out. It's kind of a little beyond the scope of the course, and that's why I'm not, testing you or judging you over it. It's just for your enlightenment. So given 3 points, so I'm going to have a point x1, f of x1, x2, f of x2, and x3, f of x3. So it's 3 arbitrary points that I'm getting. So I've got a point here, a point here, and a point here. What we're going to do with those 3 points is make a quadratic function, an arbitrary quadratic function that passes through those 3 points. So to do this, we use something called quadratic interpolation, which this is a technique that if you go on to higher level mathematics, you take numerical methods, you will talk about how to do quadratic interpolation. Okay, so once again, this is beyond the scope of the course, so don't freak out if it's not really making sense. Now, x2 here, what do we know about that middle point? It's the average of the endpoints, okay? So I average x1, x2, or x3 divided by 2 to get the x2. That's how it's defined. So it's the midpoint. Now, I'm going to define my polynomial to be f of x1 times, and then this weird looking thing, and then that weird looking thing here. The reason I have it defined like this is because if I plug in x1, I want it to output f of x1, okay? So I literally have the x1s here defined so that if I were to plug in f of x1, okay, then these terms would cancel. So if this was, if this was x1 I'm plugging in, what I really would want to happen is I would want it to output f of x1, right? That's what I would want. But in order for that to happen, I need to make sure that these things cancel out. So if I plug in an x1 here, I see that those 2 factors cancel. And if I plug in an x1 here, I see that those 2 factors cancel, and it leaves me with f of x1. Okay? So that's the first one. I call this the light switch function, all right? If I want the output to be f of x2, what do I need to happen? Well, if I plug in x2 here, I need for this part to be 0. Well, how can I make that 0? Well, if I plug in x2 here, guess what? x2 minus x2 is 0. So it doesn't matter what the rest of this is. It all goes away. It becomes 0. Pretty cool, huh? So it turns this one off. What else happens? If I plug in, let me finish writing this. So if I plug in x2 here, this makes that go to 0. Okay? This would be x2 here, and then I see that those cancel, and this would be an x2 here, and I see that those cancel. So my output will be f of x2, which is what I desire. Okay? And then for the last one, if I plug in, okay, let me pull out a little bit. If I plug in p of x3, I want it to output f of x3, right? Because every time I have an input x3, I want it to output f of x3. Okay, that's the goal, right? So that I can pass through this point here, just like I passed through that point, just like I passed through that point. So how do I do that? Well, if I plug in x3 here, what happens? This goes to 0, so that makes that whole thing go away. If I plug in x3 here, this thing goes to 0, so it makes that whole thing go away. If I plug in x3 here, then I see that that cancels with that. And if I plug x3 here, I see that that cancels with that. So all I have left is f of x3. So it's a very clever way to write a function so that it passes through those 3 points right there. So this thing right here, I don't want you to get too bogged down. There's only a couple of variables in here. Okay, so you got variables here and here, here and here, and here and here. So everywhere else, those x1s, f of x1s, all the f's, and anything with a subscript 1, 2, or 3 is a number. So don't get all hung up. This is like 3, 4, 5, 6, 7, 8, right? Those are all numbers. They're constants, okay? So only 6 variables in that whole quadratic that we've just created here. It's pretty kind of crazy, right? So what I'm going to do is I'm going to multiply this out. So I'm going to multiply the numerator out. So distribute that, and you get this right here. If you want to try to do this yourself, you can multiply it out and you'll get that. And then I do the same thing here. I'll multiply it out and I'll get that. And then again here, I'll multiply it out and I'll get this. Okay. Now, I want to do some simplification of the denominators because those are all constants, right? So I'm going to take my interval, and remember with this interval, I start at x1 and go to x3. x2 is right in the middle. So what I'm going to do is I'm going to call this distance between x1 and x2 h, and I'm going to call this distance between x2 and x3 h. And then that means that the whole distance between the two is 2h, okay? So I'm going to use that to help me out here. So this becomes h, and this becomes 2h, okay? The distance between x2 and x1 is h, and the distance between x2 and minus x3 is h. And then the distance between x3 and x1 is 2h, and x3 and x2 is h, okay? So I actually think that this should be a negative h, but that's okay. I probably just left off a negative in there. All right, so what's going to happen? Well, if I multiply the numerator out and simplify and collect like terms, I get this. If I replace things that I can replace with h, then that's what will happen, okay? And then if I multiply this out and replace things with h that I can, I get this here. And then the same thing with here, I simplify and I get this here, okay? So now what I've got is a polynomial, and I have x here, x here, x here, x here, x here, and x here. So still 6 x's I got to deal with. I'm going to integrate this polynomial over the interval from 0 to 2h, okay? H here gets me out to 2h here, okay? Remember, I'm integrating the polynomial over a to b, right? That's the idea. So the polynomial is p of x here. If I integrate this thing right here, I end up simplifying to this right here, okay? And so I'm going to convert this to be back in terms of x sub 1, x sub 2, x sub 3's. And so right here, x1 is equal to 0. Right here, x2 is equal to h, and right there, x3 is equal to 2h. So 0, and then I hop over to h, and then I hop another h, so that makes it 2h. So everywhere I see an x1, I'm going to replace that with 0. I'm sorry, everywhere I see 0, I'll put a x1. Everywhere I see a 2h, I'm going to put x3. And so everywhere I see a h, I'm going to put x2. So now I have this formula here, and I'm going to factor this to be 2 times 3 here, okay? And so now I can do this to be the whole, if I take the whole thing, x3 minus x1, and then I divide it by 2, I get the length of h, which I call delta x. So that's where my delta x comes into play, and then I multiply it by a third, same as dividing by 3. Okay? All right, so all of that to get this rule right here. Okay, delta x divided by 3 times f of x1 plus 4 times f of x2 plus f of x3. So what this says, in order to do polynomial interpolation, I do delta x divided by 3 times, I take the function value f of a, and then I multiply, and then I add, it's a weighted sum, and I'm going to weight the middle term, f of a plus b divided by 2. I'm going to do 4 times that, so I'm going to make it 4 times heavier than the endpoints, and then the last one plus f of b, okay, and then close it up. So that's what the formula is going on there. So let me back this out real quick. So in general, to use Simpson's rule, so now we've finished the proof, okay? So if you're ready, let's start back. So start back if you jumped ahead, okay? All right, so maybe you saw that whenever you fast forwarded. Okay, so in general, to use Simpson's rule, we subdivide the closed interval from a to b into n subintervals. Now, delta x is b minus a over n as usual, where n is an even number. Okay, so n subintervals. So if that's the case, we will have n divided by 2 parabolas. So like this example here, I had an interval. I subdivided it into 2 pieces. Okay, I have a piece here and a piece here, 2 subintervals. But I have remember it was n divided by 2 parabolas, right? So there's 2 divided by 2, which equals 1 parabola. So that's the 1 parabola that you have right there. Okay. All right, so what am I going to do? Well, I'm going to take approximation of the definite integral on a to b here. And I'm going to approximate it using my formula, delta x over 3 for n equal to 2. Means that I need to find the average here. So it's f of, and the endpoint here is a, plus 4 times, so I weight the middle value, 4 times f of b, a plus b divided by 2. And then the last endpoint here, f of b, right there. Okay, and so there's my parabola that's going to be used. I'm going to find the area under the curve of the parabola instead of trying an area under the curve of maybe something that I don't know how to find the area under the curve of because there's no antiderivative that exists. So if I simplify this, I'm going to replace a with x1, a plus b divided by 2 with x2, and then b with x3. And so this is my formula for n equal to 2. Okay, so if you have just this one going on here and n equals 2, then this is the formula you're going to use. Now, n equal to 4. So just in general, so that you can make sure you understand, say they're trying to, it's like integrate from 0 to 4 of f of x dx using Simpson's rule n equal to 2. The first thing you need to do is divide 0 to 4 up into 2 subintervals. Well, all you got to do is half it right there. And so now you know what x1 is, what x2 is, and what x3 is. And then you use that formula, you use this formula with n equal to 2 and plug that into your f function and you got it. That's it. So the hardest part is figuring out how to break it up, right? So like if it was something weirder, like maybe from 0 to 3, it's still the same thing. 0 to 3, I cut it into 2 pieces, so that means I got to do 1.5 here. So x1, x2, x3, just like that. Okay? When n equals 4, it kicks up just a little bit. I'm going to have delta x divided by 3 times this, which is the first part here. Okay, so it's the first part here. But then I'm going to kick it up by adding in another one. So not only do I have my parabola that I'm estimating here, I'm going to get it here eventually. But I'm also continuing this on. And maybe I get 2 more points to make it 3 points here. And I use this to approximate with another parabola. See what's going on here? And so we literally have to do it again. I'm going to use orange here so that you can tell the difference. So literally what's happening here is this second one here is the orange area, and that first one there is that red area. Okay, so you're just, when you do n equal to 4, n equal to 4 means 1, 2, 3, 4 subintervals, right? So that's the idea there, what's going on. So instead of having 2 parabolas, you've got, well, what is it? It's 4 divided by 2, which is 2 parabolas, instead of having just 1 parabola. Okay? So if I simplify all this, what happens? Well, everything has a delta x divided by 3, so I'm going to factor that out first. Now, how many f of x1s do I have? It looks like I just have one f of x1, okay? How many f of x2s do I have? So I have 4 of them here, and that's it. Okay, how many f of x3s do I have? Well, I got 1 there, but I also have 1 there, so I have 2 there. How many f of x4s do I have? I've got 4 there, and I've got nothing over there. And then I've got 1 f of x5. So the rule now becomes delta x over 3, just like it was here. F of x1 here. F of x5, oh, it doesn't really work for that, but it's still the last one has a coefficient of 1. But what's different? We go 4, then we have 2, then we have 4. Okay? So that's a pattern that's going to pop up. So that's n equal to 4. That's what the formula is. So if I do Simpson rule, n equal to 4 with your homework, it's b minus a over n, right? So that's the formula for delta x, b minus a over n, okay? So here it would be b minus a over 3n here. Okay, so you can replace that with your delta x if you want to, and then multiply by that thing there. Okay, and then everything that's in here is the same that was above here. So that is the Simpson rule formula. If you wanted to skip all of this theory and just write down this formula here, this is what you need. Okay, so this is where it's at right here. So make sure you know that formula. Just write it down. You don't have to memorize it. So now we're going to approximate the definite integral of sine of x squared, which is something that you cannot compute by hand in closed form integration. There's no closed form antiderivative that exists. You have to take calculus 2, another plug for calculus 2, in order to be able to do this with infinite series, which is actually pretty awesome. Okay, and it's not even as hard as what we just went through with all this stuff here. That's way harder than anything from Cal 1 or Cal 2. All right, so how do I do this? Well, the hardest part is dividing it up, and it's really not that bad, right? So it's an interval from 0 to 1, and I have n equal to 4. So that means I want to divide it up into 4 pieces. So that means I need 5 x's, x1, x2, x3, x4, x5. Why do I need 5? Because I need n equal to 4 subintervals. So once I divide it up on my number line, I got to figure out what are those values. Well, to do that, I need to know what delta x width is. And to do that, I do b minus a, so 1 minus 0, divided by how many there are. So 1, 2, 3, 4 subintervals. B minus a divided by n. That's a formula. So 1/4 is my delta x. So I add a fourth, I get a fourth. I add a fourth again, I get a half. I add a fourth again, I get 3/4. So these are the inputs that I'm going to plug into my function right here, where my function for this particular problem is f of x equals sine of x squared. So I'm going to be plugging in 0 squared, 1/4 squared, 1/2 squared, 3/4 squared, and then 1 squared. Okay? So plug in with your formula. B minus a, so that's b minus a divided by 3n, so that's 1 divided by 12, basically. And then I have f of x1. x1 is 0, so I'm going to plug sine of 0 squared in first. So sine of 0 squared plus 4 times the function evaluated at x2. x2 is 1/4, so I'm going to put 1/4 in here. Squared is 1/16. And then here, I put 1/2 in. I square to get 1/4. And then here, if I square 3/4, like I squared in here, I get 9/16. And I square 1, I get 1. Okay? So the coefficients matter. Here the coefficients are 1, so I don't have to write anything out in front. And here the coefficients are 2. Okay, so that takes care of all those. Now all it amounts to doing is taking a problem that is impossible to do by hand and turning it into a problem that is not bad at all. You just type it in the calculator and you get 0.3099493. Okay? The best we can do is get an approximate answer to as many decimals as we want. Using your calculator can get a better estimate of this. It uses higher than n equal to 4. Maybe it uses n equal to 40, right? It wouldn't take too many n's using Simpson's rule. Technically, your calculator, the TI-84, uses a more advanced algorithm that's even more asymptotically approaching the solution than the Simpson's rule. Okay, so it's even more efficient, but that's beyond the scope of this course. Now, this will get you something that's very close, right? It's only 100th off. It's really not even 100th off. It's like, because this would round up to 3,1, kind of like that. It's really like 1,000th off. Okay, so n equal to 4, you're already almost within 1,000th. Okay, so in general, for n even, the coefficients follow a pattern. You notice the pattern looks kind of symmetric, right? So here's the pattern. Starts with 1, then it goes to 4, then it goes to 2, then it goes to 4, then it goes to 2, then it goes to 4. It just alternates between 2 and 4, 2 and 4, 2 and 4, 2 and 4. And then a lot of stuff in between, and then 2, and then 4, and then 2, and then 4, and then it goes back to 1. So the 4 and the 1 are always together, and then we just alternate. We just end up alternating in here, okay? Lots of stuff in between going on. And 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4. All the way to 1, okay? So those are the coefficients, how they alternate. So Simpson's rule in general looks like this here.